let's start the session now. Thanks everyone for coming. So I'll introduce Steven. So Professor Steven Schockaert studied in Ghent University for his bachelor's, master's and PhD, and continued as a postdoctoral fellow until 2011, when he took up a lecturing position in Cardiff University in Wales. He became a senior lecturer in 2015 and was made a full professor 2 years later. He's won many awards, including for his PhD and various Best Paper awards, and has been very successful at raising research funds. In particular, he held a very prestigious ERC starting grant from 2015 to 2020, and also an EPSRC PI award, which started this year. Steven's published more than 200 papers and has worked on an impressive variety of topics. From the beginning, his work has combined different research areas such as uncertain reasoning and knowledge representation and machine learning. Throughout his career, he's worked a lot on fuzzy and possibilistic reasoning and spatial and temporal reasoning, but his work has touched on many different areas, including, for example, non-monotonic reasoning, Boolean games, answer set programming, and semantic relatedness. In recent years, he has worked on the interplay between symbolic reasoning and vector representations for reasoning about entities, and his talk will be on this topic. So I'm very pleased to welcome Professor Steven Schockaert.
Thank you to the organizers for inviting me. And also, my apologies that I can't be there in person. I'm actually quite jealous of the people who are there. So unfortunately, our university doesn't allow international travel still at this point. Right, so what I want to talk about is essentially about knowledge representation, right? So traditionally, knowledge representation uses symbolic representations. And then, of course, over the last couple of years, neural networks and vector representations have become more popular. And yeah, there's a certain interplay between these two types of representations. So let me just clarify a little bit more with some motivating examples. So yeah, I guess a pretty uncontroversial claim is that AI systems in many domains need world knowledge. World knowledge could be domain-specific knowledge or common sense knowledge. So most of my motivation will come from natural language processing, because that's what I've mostly been working with in the last couple of years. But I think many of the concerns will apply to computer vision and other application areas. So here's a sort of small fragment of a news story to illustrate this. So the US National Security Agency, NSA, has discovered a major flaw in Windows 10 that could have been used by hackers to create malicious software that looked legitimate. Microsoft has issued a patch and said it had seen no evidence of the bug being exploited by hackers. The issue was revealed during an NSA press conference, and it was not clear how long it had known about it before revealing it to Microsoft. So pretty sort of standard news story language that we don't have any problem understanding. But if you look, for example, at the last sentence, we have 4 repetitions of the word it. So it was not clear how long it had known about it before revealing it to Microsoft. So that's the kind of sentence that even modern natural language processing systems struggle with. And I mean, I'm not aware of any system that can correctly resolve these 4 repetitions of the word it. So essentially what sort of current natural language understanding systems can do is take the text fragment and create some kind of graph structure where we have nodes corresponding to events and nodes corresponding to entities, and they are linked with, for example, semantic roles. So here in the story, these systems would discover that well, there are 2 main events. There's a discovery event of the flaw by the NSA, and then the issue event by Microsoft of the patch. And if you look at this graph representation, there is nothing that links these 2 events explicitly together. Now, the way we read the story as a human, of course, we can infer a lot more than what is in these graph representations. For example, we know that Microsoft is the developer of Windows 10. And even if we didn't know that, we could probably infer it from the text. And we understand that the patch that was released by Microsoft was released to fix the flaw. It's not explicitly said, but it's sort of obvious. And then we know that there must have been this event, which is only implicitly mentioned, where the NSA will have privately revealed the flaw to Microsoft ahead of the patch being released. And when we have this sort of fuller picture of what's going on, then resolving the ambiguities in the last sentence, for example, become a lot more obvious. So we need knowledge, right? Factual knowledge. Microsoft is the developer of Windows 10, and we need common sense knowledge. So where is that knowledge coming from? The traditional answer is symbolic knowledge bases, and lately in particular knowledge graphs. So here you can see a screenshot from the Wikidata web interface. And you can see that indeed Wikidata tells us that Microsoft is developed by, that Windows 10 is developed by Microsoft. So that kind of knowledge we can have, with a reasonable degree of coverage from modern knowledge graphs. Common sense knowledge is a bit harder. So there's ConceptNet, which is widely used in natural language processing, that encodes common sense knowledge like a gift is capable of representing gratitude, right? It's typical sort of common sense knowledge that we may want to capture. So it contains useful information, but it's very incomplete and very noisy, right? So for example, it contains a list of things that people use for gifts. And all it mentions is that people give cakes, something small, money, a power screwdriver, and a stuffed animal. I think you'll agree that this is not a pretty comprehensive list of the types of gifts people are giving. So to summarize sort of limitations of symbolic knowledge bases is that, they are inevitably incomplete, even sort of factual knowledge graphs, but in particular, common sense knowledge graphs are very incomplete and they're also very noisy. And then, if we want to look beyond knowledge graphs and think about ontologies or rules or sort of more generic knowledge, then there's very limited amounts of that available. So that's a problem. Now, at the other side of the spectrum, if you look at sort of deep neural networks, at the moment in natural language processing, language models are sort of becoming extremely popular. Now, these language models are basically, so deep neural networks, typically 12 or 24 layers deep. And they are trained without explicit supervision signals. So what you do to train these models is you take sentences from the web, and typically a large portion of the web. You mask one of the words in the sentence. Then the sentence is represented as a sequence of vectors. So each word corresponds to a vector. And that sequence of vectors is fed to the deep neural network. Then the network outputs, again, a sequence of vectors. And that sequence so each vector in that output sequence encodes basically a probability distribution over words. And the whole network, so the word vectors and the parameters of the hidden layers, are trained such that the network is capable of predicting which word or words in the sentence was masked. Right? So there's no explicit supervision signal. All you need is a large text collection. And that's something that we have available, of course, on the web, and a lot of computing power. And then, these models can be trained. And they are huge models, right? So the biggest models these days have more than 100 billion parameters that are being trained in this way. Now, why am I mentioning this? Because one of the surprising findings is that despite this very simple training objectives, after training, these neural networks capture a lot of knowledge, factual knowledge, for example. So a simple way to see this is that if you want to find out where was Dante born, you put the sentence Dante was born in Mask, you feed it through the language model, and then the prediction for the mask is the correct answer, Florence. And it turns out that you can do this that you can extract quite a lot of factual knowledge from the language model in this way. So in some sense, the type of knowledge that you would expect to see in a typical knowledge graph is implicitly somehow captured in the parameters of these deep neural networks. And the surprising thing, perhaps, is that this also extends to a lot of common sense knowledge. It's not just factual knowledge. So this is an example from GPT-3 that's became a big hype last year, that sort of illustrates the capabilities of these modern language models. So this language model was trained to complete a certain prefix. So you give it a piece of text. So that's the text that you can see here on the slide. And then the neural network, again, that was not trained using any explicit supervision signal, other than sort of feeding it sentences from the web, it will try to complete the story. So the input is this: at the party, I poured myself a glass of lemonade, but it turned out to be too sour. So I added a little sugar. I didn't see a spoon handy, so I started with a cookie. But that turned out to be a bad idea because, okay, so that's the input that we give. And then sort of the language model completes, the cookie crumbled and made the lemonade cloudy. So I tried to fish out the crumbs with a fork, but I couldn't get them all, and I ended up drinking a lot of crumbs. So you'll see that, I mean, to be able to complete the story like this, it involves quite a significant amount of common sense understanding, and certainly common sense knowledge that goes beyond what we can find in existing symbolic knowledge bases, like ConceptNet, but also Psych and other sort of existing approaches. So, I mean, these language models have a lot of promise from the point of view of knowledge acquisition and reasoning, but they also have important limitations. One of the big limitations is essentially these models are very good at guessing. So they take sort of superficial clues from the inputs and then come up with an answer that sounds plausible. But if you use these systems, for example, for question answering, there's not really any way in which we can be sure that the answer is genuine, because these language models are known to what is called hallucinate if they don't know the answer. So you give a question, you will get an answer that sounds completely plausible, but it's made up, and of course that's a problem. And then more generally, they are deep neural networks. They are for sure black boxes, and getting explanations from these language models is extremely difficult. Also, sort of a second consideration is about reasoning, right? So these models are very good at sort of picking up the hints that are in the input text, and then coming up with some kind of representation that it involves sort of a common sense understanding to some extent of the text. But whenever we need systematic reasoning, so systematic reasoning, here you can think of the sort of inferences that you would do that involve more than one step, sort of chaining rules, for example, or types of reasoning that go beyond chaining rules. These models are simply not capable of doing that. So yeah, and I guess this is pretty uncontroversial that we have these two different ways of approaching knowledge acquisition and reasoning, which are highly complementary, and we want to understand better how the strengths, let's say, of these two approaches can be combined. So in this talk, I want to cover two topics. So the first is about whether we can use vector representations, so neural networks and other types of vector representations, as a replacement for symbolic knowledge bases. So can we somehow address the limitations of language models, for example, while keeping sort of most of the advantages? And then the second part of the talk, I will focus on using vectors to improve symbolic knowledge bases and keep using symbolic reasoning, but somehow use vectors to make that reasoning more flexible. Okay, so in terms of this first part, one of the main points, I think, is that if we want to solve the issues about lack of explainability and lack of systematic reasoning ability, we need to have a more explicit link between what the knowledge that the vectors are capturing. So we need to understand how exactly, for example, a rule can be captured using these geometric representations. Now, before I talk about rules, let's look at knowledge graphs. And so I assume most of you will be familiar with knowledge graphs. Basically, a knowledge graph is a graph where the nodes are entities, and these entities are linked with particular relationships. So what you can see here is a small fragment from the Wikidata knowledge graph. Now, there's been a lot of work on knowledge graph embedding, so learning vector representations of the entities in a knowledge graph. So basically, the idea is that every entity, so every node from the knowledge graph, is represented as a vector, typically something like a 50-dimensional vector. And for every relation in the knowledge graph, we learn a scoring function. So you can see here, FR is the scoring function associated with relation R. And that scoring function, it could be anything, but it is learned such that if you apply it to the vector representation of entity A and the vector representation of entity B, we get a high score if the triple A R B is valid. So if A is in relation R with B, and if the score is low, so below some cutoff, otherwise, right? So we want the scoring function to separate the pairs of entities that have that relationship from the remaining pairs of entities. And there are many ways in which you can do that. Let's say one of the most well-known and earliest models is trans E. So in that case, the scoring function is based on distance, so that could be Euclidean distance or Manhattan distance, between a vector offset of entity A and entity B. So basically, the relation corresponds to a vector R. So the scoring function is parameterized by this vector R, where the idea is that the relationship is a translation. So we add this translation to entity A, and if that gives us something which is sufficiently similar to entity B, we assume that A and B have relationship R. Now, one thing I want to point out is that we can basically then view relations as regions in Euclidean space. So here as a simple example, if entities are represented as one-dimensional vectors, so we can take the concatenation of the representation of A and the representation of B. So then we have this representation where the x coordinate is representing entity A, the y coordinate is representing entity B. And every point in the space represents a pair of entities, or not an actual pair, but a possible pair of entities. And those pairs that have relationship R are in, well, in this case, this region of the space. So we have this sort of cylindrical region in the space that contains those pairs of entities that have the relationship. And of course, yeah, in general, this would not be one dimension. We would have 50 dimensions for representing A, 50 dimensions for representing B, but the principle is the same. We concatenate the two vector representations. We have a single vector space, and then in that single vector space, relations are regions. So here's another example. So this is this melt. So again, relations are parameterized by a vector R, and now the scoring function is basically the component-wise products of the vector for entity A, the vector encoding the relationship, and the vector for entity B. So it's like a weighted dot product between the entity vectors, if you want. And again, the pairs of entities that have a certain relationship R are those whose representation, so the concatenation of the vectors, belongs to a particular region, which in this case looks a bit different, but the principle is the same. Okay, so now let's think about rules. So one of the reasons why, one of the main reasons why people study these knowledge graph embeddings is because they allow us to predict plausible missing knowledge from the knowledge graph. So here in the knowledge graph, there's a link that I omitted previously, which is that the Belgian national football team is has as the country associated with it Belgium. Now, if that information was actually missing from the knowledge graph, we could actually predict it from the information that you can see in green. That there's a person whose nationality is Belgian, who plays for this team, and the knowledge that this team is a national association football team. So the information in green is enough to infer the link in red. And that's the sort of patterns that knowledge graph embedding models discover. So if you don't have the link in red, we learn a knowledge graph embedding model, and then we use the scoring function for the relationship country for sports and the entity embeddings that we've learned for Belgian national football team in Belgium. We might discover that this link is actually pretty plausible, right? So that's almost like a rule, right? If we have the information in green, we would expect to see the information in red. So yeah, the research questions here are really about what are the kinds of rules that these knowledge graph embedding models can capture? And what does it actually mean for a knowledge graph embedding model to capture a rule exactly? I mean, the intuition, I suppose, is more clear, but can we make this more precise? Now, before I talk about knowledge graphs, let's first look at the simpler sort of propositional case. Because there's this theory of conceptual spaces that was in part designed to make explicit the link between symbolic knowledge and vector representations, which is what we want to do here. And the idea here is that concepts are regions, and the relationship between concepts basically captures the rules that hold between them. So as a simple example, here we have a region for the concept mammal, and we have a region for the concept vertebrate. You can see that the mammal region is included in the vertebrate region. So that means that this representation captures the rule that all mammals are vertebrates. And then, as another example, we have scary, and we have vertebrates. So we know that some vertebrates are scary, and so on, right? So it's pretty intuitive. We have regions, and the relationship, the spatial relationship of the regions captures the rules that the vector representation is capturing. Now, as I mentioned, we can think of relations in knowledge graph embedding models again as regions, so we can do something similar, right? So here's an example to illustrate this. So again, you have to imagine that on the x-axis, we have one entity, so the first entity of the pair. Y-axis is the other entity of the pair. So each point in that space corresponds to a possible pair of entities, right? So for example, here, let's say this point captures the pair lion-zebra because its projection on the x-axis gives us the representation of the entity lion. The projection on the y-axis gives us the representation for the entity zebra. Okay, and so we have a region representation for each. So that means that because this point is in the eats region, it means that according to those representations, lions eat zebras. So yeah, relations are regions in the space. Attributes of the entities themselves would be one-dimensional regions, right? So they would be, in this case, intervals of the x and the y axis. So here, for all entities that whose x value is in this range, we assume they're carnivores. They're in this range. We assume they are animals, and so on. Okay, so just like conceptual spaces represent rules by in terms of their spatial relationships, we have something similar here, right? So here we have, as an example, that the rule if x is a carnivore and x eats y, then it holds that y is an animal. So that rule is captured by this representation. Why? Because whenever we pick a point, which is such that the projection on the x-axis is in the carnivore region, and such that the point is in the orange eats region, then it will always be the case that the projection of that point on the y-axis is in the animal region, the animal interval. Yeah. So that means that yeah, this rule is satisfied. In a way, it's very similar to what we have in conceptual spaces. Now, why does this matter? So the main motivation, I think, is for inductive knowledge graph completion. So the idea is this. Suppose we have already learned an embedding. We already have a representation of the relationships. So for each relation, we have these regions. And for all the entities in our initial knowledge graph, we already have a vector representation. Now, we want the representation to be such that if we then add a vector representation for a previously unseen entity, that the knowledge that we infer about that unseen entity is somehow sensible, let's say logically consistent or yeah, meaningful. And with this representation, we do have that, yeah, for a previously unseen entity x, if we choose its embedding such that its projection on the x-axis is in the carnivore region, then we can only have that entity x would be predicted to eat an other entity y if that other entity y is in the animal region. Right? So it's like the same I explained on the previous slide, but just sort of from the point of view of how we would use this in sort of inductive knowledge graph completion. So we want these rules to be satisfied because it guarantees that whatever other entity representations we add, the set of facts that we predict would always be logically consistent, or at least in accordance to the rules that we want the model to capture. So here's another example with an existential. So if x is a carnivore, then it is always the case that there exists some y such that the pair xy is in the eats region and the y coordinate is in the animal region. So just as an example of an existential rule. So we have a natural way of defining what it means for a knowledge graph embedding model to capture a rule. I mean, natural in the sense that it closely corresponds to conceptual spaces. So the next question is, can existing models capture rules in this way? And the answer is mostly negative. So here's one result to illustrate this. So this is bilinear models. So any model which we can write like this. So the scoring function for entity A and B is the product of the entity representation for A, a matrix representation for the relation R, and an entity representation for the entity B. Right. So this model is a special case of this, but there are many other models that are special cases of this bilinear framework. Now it turns out if you allow this particular model, then there are severe limitations on the sets of rules that can be jointly modeled by the knowledge graph embedding model. So to illustrate this, suppose we have these rules. So we have relationship R1 to Rk, which are all sort of sub-relations of S, right? This is subsumed by S. So we can graphically see this like that. So we have R1 to Rk, which are sort of special cases of relation relation S. Then it turns out that we can only model this with bilinear knowledge graph embedding models if, well, there are these particular permutations which basically tell us that rather than having this hierarchy of K separations, what we have is really at most two change of relationships, which are special cases of S. So we cannot have three relationships which are special cases of S, but which are not special cases of each other. So that's, I mean, seems like a pretty severe theoretical limitation. To what extent it matters in practice is another question, but it's I think, yeah, quite notable. I mean, there's many limitations of other models as well, and we also have a semi-positive result, which is like this. So the idea is that we consider rules like this. So existential rules. So each of these atoms is a first-order atom. So a relation with a number of arguments, which could be variables or constants. So this is the general syntax of an existential rule. And the only limitation we impose is that for any atom here in the body of the rule, it can share at most one variable with the atoms that come before it. Right? So it means that if you think about the dependency structure if you think of the body of the rule as a path, we cannot have cycles. It's basically what it's saying. Now, it turns out that if you allow relationships to be modeled by arbitrary convex polytopes, so the intersection of a finite number of half spaces, so essentially convex regions, then any set of existential rules of this particular form can be modeled. A consistent set can be modeled. Exactly. But if you don't have that quasi-change condition, then that's no longer the case. So we have a positive result in the sense that at least we are guaranteed a relatively general set of rules or type of rules can be exactly captured by the embedding. But even by allowing arbitrary convex polytopes, which is a pretty general condition, we still cannot model arbitrary existential rules. So one of the things we may wonder is if the reason for these negative results comes from the fact that our definition of what it means for an embedding to capture a rule, perhaps that's too strict in some sense. So more recently, I looked at a more perhaps flexible framework or less demanding notion of satisfying a rule. And it's again motivated by this idea of inductive knowledge graph completion. So suppose we have a common sense knowledge graph, and we have an embedding of that knowledge graph, which means that we already have a vector representation of wings, feathers, flying, and we have a scoring function for the relationship has part and capable of. So basically, we understand what it means in terms of the vector representation to have wings, to have feathers, and to be capable of flying. And now we have a new entity E, and the only thing we know about that entity is that it has wings, it has feathers, and it's capable of flying. Now we want to learn a vector representation of E based on that knowledge. And well, we want the model basically to be able to infer that based on this knowledge, probably E is a bird, and E is capable of laying eggs, and so on and so on. Right? So yeah, the way the framework looks is like this. So we have knowledge, and we can think of, even though here I showed this as sort of a knowledge graph triples, really, because all this is known, we can think of this as a proposition, right? As an attribute, having wings, having feathers. So we have input attributes for entity E. We're going to assume that for each attribute, we have a vector representation, and that the vector representation that we're going to learn for entity E is obtained by somehow pooling the vector representations of its known attributes. And then, well, we have a scoring function that allows us to predict from a given entity what attributes it has. So let's call this the decoder. And what we want is that at the output of this process, we find that E is a bird and E is capable of laying eggs, right? So that's now what we mean, for example, by capturing the rule: if the attributes has wings, has feathers, and could fly are satisfied, then the attributes is bird should also be satisfied, right? So if these are the attributes that go into our encoder, then we want to be able to, then we want the resulting entity vector to be such that the attribute is bird is predicted. Okay, so how does this work? So as I mentioned, we're going to assume that every attribute is represented by a vector, which we assume to be given, and that the entity vector is obtained by pooling these attribute vectors. And of course, there are many ways in which we can do this. One of the most common ways is to take an average of the attributes. And well, there's a number of other alternatives that I've considered. So instead of the average, we can take a normalized average. So we add up the vectors and then ensure that the Euclidean norm is 1. This is the pooling function that's basically used by models like skipgram. So it's pretty popular. And this is max pooling, which is also very often used in neural network models. So these embedding functions define how we go from the attribute vectors to the entity vector. And then we have the labeling functions that tell us how we go from the learned entity vector to the attributes that we want to predict. And so by far the most popular thing to do is to basically assume that for every attribute there's a linear classifier. Right? So that's what this labeling function tells us. Another possibility is to have a distance-based approach. So if that entity vector is sufficiently close to, let's say, a prototype of attribute B, then we assume the attribute applies. And then there's 2 more conditions which I studied for specific technical reasons. So what about the results? So I'm not going to go into detail, but so what I looked at is for different combinations of embeddings and labeling, so embedding methods, so pooling functions, let's say, and labeling functions, is it possible, in theory, to capture arbitrary sets of monotonic rules, right? So propositional rules, I mean, without negation and disjunction. But for an arbitrary propositional knowledge base, can we simulate, I mean, can we learn embedding, which is such that the rules satisfied by the embedding are exactly the rules entailed, so the Horn rules entailed by the propositional knowledge base. And then I did the same for non-monotonic reasoning. So using the possibilistic logic semantics. So here the question is, can we learn an embedding such that the rules satisfied by the embedding, so in the way I explained before, are exactly sort of the default rules modeled by the possibilistic logic theory. Okay, so what are the results? First of all, a lot of negative results, right? So for most of the, let's say for the most commonly used embedding strategies, we can find counterexamples that show that certain combinations of I mean, simple combinations of Horn rules can never be modeled by that embedding strategy. But then, there's also positive results, in particular 2 approaches that are able not only to simulate, let's say, propositional reasoning, but also sort of this default reasoning with the sort of usual ranking semantics. So that's at least a positive result. The caveat here is that these, I mean, the constructions that show that this is possible rely on sort of using very, very high, I mean, using very large constants, exponentially large constants, which means that in practice, neural networks cannot realistically exploit similar constructs. And the theoretical possibility of this particular approach in practice may not really make much sense. So even though these models are capable theoretically of modeling arbitrary propositional rules, they may not be the right combination of embedding and labeling functions for neural networks or embedding strategies to learn these rules effectively in practice. So that's one of the reasons why there seems to be a mismatch between the strategies that are often used in practice and the strategies which are sort of which seem to have the most important theoretical properties, or at least are provably general in some sense. Okay, so that's sort of concludes the first part. The second part, which will be shorter, is about using vectors to improve symbolic knowledge bases. And now the intuition here is that regardless of how far we can take this idea of using vectors and vector representation and neural networks to simulate reasoning and knowledge bases, the need for interpretability in certain applications means that sometimes there is no alternative to rule-based methods. And I think that's, again, pretty uncontroversial statement. And now, the problem with one of the problems with rules is that, because, I mean, even for applications like knowledge graph completion, there are rule-based methods these days which are pretty powerful. There's a method called AnyBurl, for example, which is capable to get pretty competitive results on typical knowledge graph embedding benchmarks. But the limitation of these rule learning strategies is always that you can only learn rules which are covered by the training data, right? So for every rule that you're learning, you need sufficient examples of cases or entities or whatever you're modeling that satisfy both the body and the conclusion of your rule. Neural network learning is not like that. Neural networks somehow are capable of doing this interpolation between situations that are covered by the training data. And so one of the questions is, can we do something similar in the symbolic domain? Now, to illustrate this, this notion of interpolating rules, let's look at this example, right? So suppose we have a rule that tells us that tomatoes contain vitamin B6 and mushrooms contain vitamin B6, then we can plausibly infer that carrots contain vitamin B6. So this is known, I mean, a type of inference which is well studied in the cognitive science literature, what is known as category-based induction. But as I mentioned, it also closely corresponds to sort of a certain type of neural network learning. The point is that there is very little tomatoes and mushrooms have in common that would not be shared by carrots as well, right? So that's intuitively the reason why we believe this to be a plausible inference. On the other hand, if we look at this version, kale contains vitamin B6 and spinach contains vitamin B6, then the conclusion that carrots contain vitamin B6 becomes less strong, right? We may still think it is plausible, but certainly it's less strong. And the reason here is that kale and spinach are quite similar, right? There's a lot of things that they share. They're green leafy vegetables, which are not shared by carrots. Now, how can we measure that degree of strength? How can we work out that this is a more plausible conclusion than this? Now, we can use taxonomies, for example, but the existing taxonomies are not sufficiently fine-grained to be able to do that. So this is, again, a fragment of Wikidata. And Wikidata can tell us that spinach and kale and carrots and so on are vegetables, but it doesn't give us any hints that spinach and kale are more similar to each other than carrots and tomatoes. So the idea is to use, again, vectors to solve that situation. If you look at a vector space, we have representation of carrots, tomatoes, mushrooms, and the idea is that if you take the premises, so we have a rule about tomatoes and mushrooms, and we generalize this to sort of a region in the space, then carrots will be in that same region, and that's intuitively why how we can infer using vector representation that this is a plausible rule. So the question is, I mean, does this work in practice? So this is work we did a couple of years ago, where we looked at vector representations of, well, in this case, focusing on place types. And we were simply looking at triples of concepts, where one concept was geometrically in the vector space, somehow in between or closely to sort of the region in between the two given concepts. So for example, if we have the representation for castle and chapel, then in the middle region, we have abbey. Between restaurant and tea room, we have bistro. Between marketplace and slaughterhouse, we have butcher shop. Between greenhouse and playhouse, we have conservatory, and so on. So these, it's not perfect, but in many cases, these between this relationship capture really quite intuitive, well, sort of common sense knowledge about how different concepts are related. And then it turns out that also in practice, we can use this type of reasoning for ontology completion. So we had some papers 2 years ago about this. The idea is basically this, right? So we take an ontology, and and we look for rules that have the same structure, except that they differ in one argument, right? So for example, we have a rule involving some predicate R1 and some predicate R2, and then we know that rule sort of holds for orange, but also holds if we replace orange by lemon or by grapefruit. Now, we don't need to know what R1 and R2 are to infer that probably that same rule is going to hold for lime, for example, right? So what we do is simply look for sets of rules in the ontology that have the same structure, differing in one concept. We take the vector representations of these concepts to define a region in the vector space, and then we look at what other concepts have a representation in that same region, and then we infer these rules as being plausible. So I'm not going to go into any detail, but this allows us to infer plausible missing rules in a meaningful way. We can also do it with analogies. So here's an example. So suppose we have, it's the same story, right? We have a bunch of rules that have the same structure, but now they differ in two arguments. But the point is that there's an analogy between sort of how the arguments change. So we have something, bat, cave. Then we have the same rule, but with duck, pond, and dolphin, sea. So we don't need to know what R1 refers to. Here it's sort of intuitively, it's something like lives in, right? We don't need to know that because we can discover this analogical relationship from vector representations again. And so without knowing what R1 refers to, we can infer that this rule, Trout River, for example, is also plausible. And again, so that sort of allows us to predict missing rules and ontologies in a meaningful way. The key here, of course, is that we need to be able to discover these analogical relationships. And that's something that, particularly lately with these language models, also has become a lot more feasible. So if you're interested in this, we have a paper at EMNLP this year where we show how language models can be fine-tuned to model these analogical relationships and how we can sort of get human level performance in solving analogy questions. Okay, so that's sort of rules. Before I finish, I just want to say something about sort of concept representation, because if we talk about improving symbolic knowledge bases, often it's also about improving the representation of concepts. Now, this can be done pretty naturally with vector spaces as well. So here, what you can see is vector representations of entities in Wikidata that have as their semantic type location. So all the dots that you can see are locations. And in red, you can see those entities which specifically are known to be train stations. And now, so this is a two-dimensional projection of a 300-dimensional space. That's obviously in 300 dimensions. Other things are going on, but what you can already see in this two-dimensional projection is that the train stations are really clustered together, right? So what we can do is, based on the known examples of train stations, we can learn this region in the vector space to model the concept train station, and then any other entity, any other location that has a representation in that same part of the vector space, we can then infer to be plausibly a train station as well. So we can use this to sort of automatically complete, let's say, the A box of an ontology or a knowledge graph. Now, the problem is that here this works really well because we have a lot of examples of locations, and we also have a lot of examples of train stations. But for many concepts, we only have a few examples, let's say 2, 3, 4, 5. And you have to bear in mind that we are working in a high dimensional space, let's say a 300-dimensional space. So if we do something like taking the convex hull, or let's say a Gaussian that sort of is sort of focusing on these few examples, then the coverage of that concept that we're learning is going to be only a tiny fraction of our vector space, right? So this is illustrated here with this toy example. Suppose these red squares are examples that we have of concept C, where we can learn a region which is going to be quite small, right? And then we have other concepts. And again, the region that we're going to learn is sort of centered around the specific examples that we have. But then in this toy example, all the black dots are supposed to be entities whose type is unknown. And we can't really make any meaningful predictions about whether these might be plausible instances of any of these concepts of interest, because they are not near these regions that we've learned, the models of the concept that we have. Now, the solution, or a partial solution that we looked at, is to use something called conceptual neighborhoods. So the idea is that often, if we have a pair of concepts, we think of these, a pair of related concepts, we think of these concepts as being disjoint, but at the same time, we can imagine there to be borderland cases in between these two concepts. And in those cases, intuitively, we would expect the vector representation, the region modeling this concept, to be adjacent in the vector space. Now, suppose we know that concept C is, and so this is what we call conceptual neighborhood. So that suppose we know that N1, N2, N3, and N4 are conceptual neighbors of concept C, then actually we can do much better than learning a concept like this. We can sort of carve up the space and assume that, well, essentially anything that's closer to concept C than to concepts N1, N2, N3, or N4 must be sort of an instance of concept C. Now, it turns out that we can learn these conceptual neighborhood relations from text reasonably accurately. So, for example, here are some examples of conceptual neighborhood relations that we discovered. Yeah, they are not perfect, but most of them make sense, right? For example, novel short story is, I think, a good example. We think of them as disjoint, but clearly we can imagine a borderland case between short story and novel. Lake or river, so if you have a river that becomes very wide, at what point does it become a lake? Child, man, obviously also a clear example of this. And then it turns out, if we apply this idea of conceptual neighborhoods to get better concept representations, then we can also, experimental results show that this lead to more accurate predictions. So here's maybe just an example to illustrate. So this is from the actual experiments that we did. So the dots are training examples. So the red dots are training examples of the concept songbook. And then we have guidebook and brochure. And then the crosses are test examples that we try to classify. And you can see, for example, these test examples, which are somehow in the middle, they are not similar to any of the training examples that we were given. So traditional concept learning strategies would not classify these instances correctly. But once we discover that songbook is a conceptual neighbor of guidebook, then basically we carve up the space around here, right? And so these test examples are then classified correctly. All right, so let me conclude. So in terms of the first part of the presentation, can we use vector representations to replace symbolic knowledge? So there's obviously a lot of open questions. One of the more puzzling aspects is that embedding models that are used in practice and that perform best in practice are not typically the ones that are most expressive in terms of the kinds of rules that can be modeled. In terms of theoretical properties, propositional rules, we can model in principle, but proper relational rules seem to need more structure. So this basic idea of entity embeddings does not seem capable in general of capturing arbitrary relational rules. So what I think is needed now is to develop a hybrid framework that somehow keeps vector representation, that adds more structure, and that somehow allows us to model arbitrary relational rules. Graph neural networks seem like an obvious candidate for this, but even graph neural networks have similar limitations to the limitation I identified with sort of not allowing cycles in the body of rules. Using vector representations for improving symbolic knowledge. There are several promising things that we can do. So we can make reasoning more flexible. We can add plausible missing knowledge. But still, of course, the resulting framework is not as flexible as neural networks. So there's a gap between the flexibility, let's say, and the inductive capability of neural networks and what we can do with rules. And again, I think that means that we need to develop, one way or another, hybrid frameworks that allow us to sort of balance that trade-off a bit more carefully. So the trade-off, let's say, between flexibility, generality, and interpretability, and we seem to need something somehow a bit more in between rules and neural networks. So let me just finish by saying that as was mentioned at the introduction, I have a project that looks at some of the questions I talked about, especially this idea of learning to systematically reason about geometric representations of properties and relations. So this is sort of the main goal of the project. If you are interested in this and are looking for a postdoc position, I will be advertising something in the next few weeks. So yeah, I would say please get in touch. Thank you very much for your attention.
Thanks very much, Steve, for a really interesting talk. Do we have any questions from either the room here? Oh, I can see a question already from Nico. Can you unmute yourself, Nico? Or do I have to do that? Oh,
no,
that's great.
Thank you.
Thanks.
So I wrote down several questions, but let me just ask one. So one thing I was wondering about, so I really like this interpolation idea, but then what I was wondering is, it seems that it really depends on the representation that you learn. So dependent on your data and even the embedding dimension, the convexity assumption may be true or may not be true, right? Because I think interpolation really depends on the assumption that everything is convex, right? So I don't know, do you have any ideas how to overcome this problem, or do you already have a solution for that?
I think sort of convexity, I don't think is a problem. I mean, so it's predicted by conceptual spaces. It's in these cognitive, let's say, representations of models. The convexity assumption seems to be satisfied in domains where this can be verified. And for neural network models, I've seen no evidence that the kind of embeddings that are used in practice, that convexity assumption is violated. Now, the point is that convexity in a 300-dimensional space is not as strict as it seems. So if you think about convexity in 2 dimensions, it seems like a very strong assumption. But if we have a 300-dimensional space, and we have typically, if we model every word in language, we have a few 100,000 vectors. But a few 100,000 vectors in a 300-dimensional space, that's pretty sparse sort of coverage of your space. So almost any set of let's say 100 vectors would define a convex region that doesn't really contain anything else.
So if I just think about this example where you say something contains vitamin B6, and then say you take all your entities where you know that they contain vitamin B6, and if I understood correctly, for these interpolation rules, you take the convex hull, and then for everything in the convex hull, you say it also contains vitamin B6, right? So then I wonder, if you take all the entities that are in the convex hull, how many percent of these entities do really contain vitamin B6? Have you made experiments like that?
Yeah. I mean, not for vitamin B6. That's a toy example.
Yeah. Okay. Sure.
but yes, we had several papers where we looked at a box induction, right? So we did experiments with Wikidata and BabelNet. So you take a concept, you take the instances of that concept, you hold out 20% of the instances, you learn representation from the remaining 80%, and then you see whether you can predict which are the 20% missing instances of that concept. So yeah, I mean, the results are it's not perfect, but it's difficult to sort of give an exact figure on how well it works, because obviously the knowledge bases are not perfect either, right? So some of the things that you're adding may not be in your initial knowledge base, but they're actually correct. So to summarize, it's definitely not perfect. It's not that we can magically sort of add knowledge that's always going to be correct, but it's useful enough, I think, to be considered. And to be considered could mean if you're looking to extend the knowledge base, then this could be sort of examples you give to the ontology constructor, I mean, the knowledge engineer, to manually verify. But usually what is going on is that you use this as part of maybe a natural language processing system, which is going to be noise tolerant anyway. And the question is about, can you improve sort of the downstream performance on a particular task? The other part to your question about the nature of the vector space is that I think a big unanswered question is this idea that, of course, the representation of an entity has intuitively multiple different facets, right? Things can be similar in one context and very dissimilar in another context. And the intuitive solution to that is not to learn a single vector space, but to have multiple vector space representations that cover different facets. So a typical example would be, if you're modeling buildings, then two buildings could be similar because they're both universities. Or they could be similar because they're both in the same city. And this two types of similarity which have nothing to do with each other. And if you're learning a concept, the first question is, what aspect of similarity do you need? So I did some work with the PhD students over the last couple of years on whether we can try to learn representations of vectors that have these sort of multiple facets, and then you use that to improve sort of concept induction by intuitively, first of all, determining what is the facet that we're looking at, and then doing the concept interpolation in the correct facet of the vector space. So that's something that can be done. Again, to some extent, it has problems of its own, but yes, it is an important research question, I'd say.
Thank you.
Thank you. Tony has a question, I think.
Hi, I'd like to ask about the experiments you do when you're learning logical formulae. How do you evaluate them? Do you get crowdsourcing in advance to give you lots of rules and you see whether you get good coverage, or do you judge them afterwards? People mark them, whether they're good rules or bad rules?
No, in the experiments we've done, usually we've looked at sort of typical held out sort of test sets. So we take an ontology, we take sort of 20% of the rules, or a third of the rules that we remove. We learn the representation, or we do whatever we do. And then we take the correct rules, and then we have corrupted version of the correct rules. And then you get your model to rank the rules. And you evaluate and you compare models based on how well they can separate sort of correct rules from corrupted rules.
So is this going to be a limitation going forward if you wanted to, for example, learn rules that are not in an ontology, other kinds of first order logic formulae, and there aren't really corpora of these kinds of formulae? And going forward, would that be something that needs to be addressed, perhaps by crowdsourcing?
Yeah. I mean, what often is done is that, so you start with an evaluation like that, and then to see whether you can discover new knowledge, you take the full knowledge base, you predict rules, and then you take the top 100, and then you get people to manually score these. Something we haven't done, but in other domains, it is often, other people have done that. There's a big, but the question of to what extent we can discover new knowledge is difficult to answer, because it's particularly sort of in the context of common sense knowledge bases. It's particularly a prominent question, right? So there's been lots of papers that show that we can use language models, recently especially language models, to predict missing triples in concept nets. So to discover new common sense knowledge beyond what is already there. But the problem is that what is new knowledge, right? Clearly, language models are very good at discovering paraphrases, so phrases that basically mean the same thing. So you can have lots of triples that are not mentioned in concept nets, but they're almost like sort of rephrasing, because especially if you have events, then there's different ways of phrasing the same thing, and what you end up predicting are variations of what was already there, rather than genuinely new knowledge, and that's more difficult to analyze, right? You can verify that the knowledge that you predict is not there, and you can manually verify that that's correct, or how often it's correct. But then, to what extent are you inventing and discovering new knowledge, and to what extent are you sort of adding variations of what you already knew anyway? Then, yeah, that's more difficult
Thank you.
Okay, thanks very much. At this point, I think we're sort of beginning.
One question, maybe.
So,
yes, can I ask a question?
Ulrike, do you ask a quick question?
Okay. Thank you, Steven, for this very nice talk. Just, I was wondering, okay, you have been using many things, I mean, conceptual space, analogy, betweenness, and things like that, but with using the embedding representation. But I was wondering if there is a way of cooperation between representation of different levels. For instance, you may have the analogical relation which holds at the embedding level, but it may hold at a much more abstract level where you have just a conceptual representation of the items. Do you see some way of cooperating between different level of granularity in the representation, in the knowledge representation, or it does not make sense for you?
I mean, no, it makes sense. It's a general question, I guess. I mean, so
yeah, sure.
Not so much interpolation, but so I have a project that's about to start in a few months now that will focus on interpolation between rules that have a different structure. I think that's related to your question, where we don't do the interpolation because we have one concept that sits in the middle of two other concepts, but we have rules or inference patterns that describe some situation, and we have another situation, and then we're trying to model that a new situation is in between these other situations. So the typical example would be if you do link prediction in social networks, right? So you only have one predicate. Let's say friends, right? This person is friends with this, and you have a graph, a subgraph that corresponds to friendship. And you know that if in that kind of structure, you can predict a certain property, let's say. And then you have a slightly different graph, and then you know, interpolation works at the graph level. We want to find graphs of let's say friendship graphs that are in between to other situations. And that's it's an open question how to do that, right? Because the intuition of interpolation would mean that we need a vector representation now of conceptual structures or graphs. For analogy, I think it's the same. That's we want to model analogies between situations, which at least we can think of as at least to the point where we can think of situations as graphs with different relationships between entities. That then, I see some hope in sort of lifting the concept level strategies that we have now to sort of more general things. But that's future work, I would say.
Okay, thank you, Steven.
Thanks very much. Thanks, Steven, again. I think lots of connections with default logics and there were things I was wondering about, sort of things to do with strengths of inference, but it's time for the coffee break now, unfortunately. So for those watching from home, do make yourself a nice coffee and have a cake, as we've got some very nice ones here too. And we'll be starting again at 10:30. And I don't know whether you're free, Steve, but I mean that there may be the possibility of people continuing discussion online, if you like.
And obviously, people are more than happy, more than welcome to get in touch. Unfortunately, I have to go. I have to take my children to the dentist now, so I can't stay for the coffee break. Yes, I mean, do feel free to get in touch, and I'm very happy to continue discussing.
Thanks. I hope that trip goes smoothly. Thanks again. That's great. Okay. Bye-bye.